Good morning, one and all. Session will start within these two minutes. Good morning, one and all. My name is Shivaraj Kumar S, Assistant Professor, Department of Chemistry, DBIT. Welcome you all for the fourth day of FDP on recent trends in green chemistry 2021. Now, I would like to introduce speaker of today's session, Dr. P. Lalitha, Professor of Chemistry, Avinashilingam Institute for Home Science and Higher Education for Women, Coimbatore. Madam has done MSc, MPhil, PhD, and CSIR NET. Her specializations are organic synthesis, nanosynthesis, photochemical isolation of compounds, drug conjugation studies, adsorption, sensors, and cyclic voltammetry. Awards and achievements are Best Faculty Award, Sri P.K. Das Memorial Award for Faculty of Chemistry in 2009 by Nehru College of Education and Charitable Trust. Best NSS Unit Award as the Program Officer for Unit 7 on the NSS Day celebrations organized by the NSS cell of Avinashilingam Deemed University for Women in the year 2010. And first prize in Best Oral Presentation in InnoForum 2, an international conference for the paper entitled In Vitro Evaluation of Sun Protection Factor of Nanoparticle Incorporated Sunscreen Lotion at Bhopal during February 11, 2017 among 11 countries and 200 participants, who won the gold medal in UG and PG and awarded CSIR NET certificate. Madam has guided for many PhD students. With the brief introduction, now I invite Dr. P. Lalitha Madam to take over the session in topic supercritical carbon dioxide extraction, a paradigm shift in extraction technology and sustainability. Madam, please take over the session.
Ma'am? Lalitha ma'am, you are
Yes.
yes ma'am, you are presenter now. You can start. Thank you. I was trying to send a message to you. No problem.
Yes, ma'am. Thank you so much, ma'am.
So good morning to all the organizers and participants. And it gives me great pleasure to be a part of this faculty development program. And before I begin this session, I would like to thank the organizers, the head of the department, Dr. Manjunatha, and Dr. Krishnaveni, Dr. Shivaraj Kumar, and who assisted me in this trial session, and also Dr. Sushma for giving me this opportunity. So it is nice to see a group of faculty. I think they're all from engineering colleges. So I will be touching upon the basics because I do not know how far this topic will be helpful. But maybe even in theoretical work, this can be used. So I thought I will talk something about a different topic. And as I was mentioning in the trial session, in fact, it is also a learning for us. We too start learning different topics or update our knowledge only when such opportunities come to us. So with this, I will begin my session. So before that, I thought I will give a small, I have a small presentation, maybe a minute video about the facilities which we have in our university and which we are extending to the researchers in and out of the our state. And in fact, we have reached even to the northern states also. So the facilities which are available in Avinashilingam, it is not only thrown open to our researchers, but any researcher, if they find it will be helpful, they can send their samples through courier or through any known person, and even consultancy services they can avail, because research or any output, it stops at one stage because we don't have the access and facilities. So with that thought, we have initiated this. Our institution has also instituted a centralized facility. So I will be sharing a very small video. So I think the video is seen. Yes, sir. Yeah.
Yes,
I'm not sure whether the audio of the video will be heard. If the audio is not heard, I can just give the background voice.
Audio, we cannot able to hear, ma'am.
Yeah, so I will go the background voice. So I'm just taking you all to the on a virtual tour to the Professor C.N.R. Rao Research Center, which is a centralized research facility of our university. So this center houses very few equipments only, but they are sophisticated and it caters to the research needs, particularly material science research. So it caters to many of the fields of science and technology, even to engineering. We do have field emission scanning electron microscope, which is used for morphology study and for determining the EDS, means the elements present in the sample and the size and shape of your particle. Then we have a powder XRD, where you can find out whether the material which you are testing is amorphous or crystalline or above the lattice structure, and so many other details you can get. It is also a fingerprinting technique. So again, you have FTIR, which is a common instrument which organic people they know, and even now inorganic people have started using it. So it will tell us about the functional groups present in a material, and you have profilometer, which also gives you the topography in a 3-dimension. And if any of you all happen to come to Coimbatore, please do visit our institution where you can get your body composition profiled. You might have seen this equipment in the hospitals, but it is available to academic users and researchers who visit our university. It's a sensor-based instrument which will give you the profile of your body, like the calcium content, moisture content, lipid, protein, etc. It is a non-invasive technique. We need not draw blood or urine, etc. It's just a sensor-based one. So if any of the engineering people are dealing with the thin films which are colored or textiles material, we do have a UV spectrophotometer with the Color Lab software. It is COLOR, Color Lab software. The name of the software is Color Lab. So that gives you some matching and reflectance studies is possible. And next to that, you can see the person who's sitting there is working with Color Lab software. At the back of her, you can see an equipment which I have covered and kept. That is a texture analyzer. If you have any material whose texture, smoothness and breakability and all, if you want to see, you can use the texture. And many of us now we have started working on nanotechnology, and those who are into nano, they really know that just like organic synthesis, even if you start with a little bulk quantity, you end up only in very little product. So very few milligrams only you get. So bulk preparation of nano is a bit tedious task, but we do have a nano spray dryer wherein you can give us a solution around 200 to 500 ml and it will be sprayed. It's an atomization mechanism. To give you a small example, if you take 500 ml of milk, you can get milk powder. So based on the nozzle size, you are able to get different sizes, nano sizes. We are given with 3 options, so you can prepare different nano sized particles. And the plasma chamber, we all know it is for some sitting. Then commonly used is a thermogravimetric analyzer. We do have the thermogravimetric analyzer coupled with DTA. Some of us may be using it. We know that it is for temperature, knowing the stability of the sample. We can heat up to 1100 degrees Celsius in the equipment which we have. And we do have like platinum and alumina crucibles which can withstand temperature, aluminium, etc. with up to 1100 degrees Celsius. And homogenizer is something very common to us. And atomic absorption spectrophotometer and ball mill. So ball mill is also a physical method of, we can say it is an top-down approach of preparing nanoparticles. Like you cut down from bulk material and you can grind it and you will get it as a nano-sized material. So up to 1.5 kilograms is the capacity of the ball mill which we have. So we have named this research center as Bharat Ratna Professor C.N.R. Rao Research Center because we all know he's a world-renowned scientist, and I also happened to meet him in Bangalore. He's in your place only, called Jakkur, which is near the, I think, a few kilometers away from the airport. So they have the Jawaharlal Nehru Advanced Center. No? There are several research scholars are being motivated by Professor C.N.R. Rao and inspired by his you can see that we have kept all the laurels of Professor C.N.R. Rao. In fact, I found that he has got several degrees, more than 580 degrees. In fact, when I went there to the museum, they have an underground museum in the Jawaharlal Nehru Center for Advanced Research, where with the prior permission, we hired a photographer and we went inside. They allowed us to take some photos because I'm repeating that is with prior permission. And I could see some of the degrees. You can see what are the photos or the frames, what you see here are some of his degrees and laurels. I said some because I started counting how many PhD degrees he has. I was able to count up to 81 or 83 and then I became tired, so I left. So the number of DSCs, you can imagine he has got even more than 80 DSCs and internationally throughout he has got. So we wanted to have such an eminent personality inaugurate this center, and we also had we are privileged to have him. So that was a short introduction about the research facilities which we have in our university, and this I have showed you also that any researcher who feels that research is not accessible to them because equipment facilities are not available, now they will know that such centers are also offering are outsourcing their equipment facilities, and even in Bangalore you have several institutes, and all over India also you do have some centers, sophisticated centers like IIT Chennai and so many other institutes are offering that. Only thing is that we have to take effort on our side and motivate research scholars. And I think I'm sharing my presentation. Any one participant to tell whether the slide is seen? Or organizers to say whether the slide is seen?
No, madam. Just move. Yes, madam. Now it's showing.
Yeah, I'm just showing some
yes.
images.
Yes, madam.
Yeah. Okay. So I think participants can't interact, no, sir?
Yes, madam. They will.
Okay. In fact, I thought I will just ask them a question, no issues. But what you see is all of us might have guessed that it is nothing but dry ice. So in many of the movies, when they show heaven on earth, there you might have seen fumes at the back of the hero and heroines, and even in school functions and in auditoriums, they have started using dry ice. So dry ice is nothing but liquid carbon dioxide. So the applications of this liquid carbon dioxide fascinated me to take up this topic, which is supercritical carbon dioxide extraction. And I wanted to tell that there's a paradigm shift in this extraction technology, in the general extraction of the traditional technology methods. And there's a role of the sustainability when we speak of this extraction technology. So let me begin my lecture. And before I go into the carbon dioxide extraction technology, we should know that why I mentioned it as sustainable technology. The reason is because it is one of the techniques which comes under green synthesis. So way back, I think 10 to 12 years ago, this green synthesis is of great concern because environmental pollution was more, and it was alarming that everybody started to form forums to discuss a need to protect our Mother Earth. And then came this sort of green, the coining of green, and everywhere it was green. Like now everywhere it is nano. Earlier it was everywhere it was green. So, yeah, and if I'm not wrong, I remember even a few institutes started courses on MSc green chemistry. Like once we had MSc environmental chemistry, they even started MSc green chemistry. And then you might have seen green chemistry forums started developing throughout, and even journal names were green chemistry journal. And then you have principles of green chemistry, like you have 12 principles which speak about the methods or rules which we need to follow to maintain our environment. So what exactly is green synthesis? So when it comes to preparation, we need to adopt some green chemistry principles. I said there are 12 principles in synthesis, so we need to adopt some of the principles. One such green principle is that we should avoid using carcinogenic or non-environmental friendly solvents. As we all know that 10 to 15 years back, if you see the practicals of several PG courses, they might have used several solvents like benzene. I do not know whether some of us might have done, even I have done that experiment, partition coefficient experiment involving benzene and CCl4 and all. But then after that, when benzene was banned because it is a carcinogenic solvent, we have removed that experiment from this curriculum, and we have replaced it with some other experiment which is little environmental friendly. And now we are slowly replacing, and we are going in for mini tools or recycle, reuse process, and we never go in for hazardous waste. Therefore, one of the principles which is advocated in this green chemistry principles is that we have to use eco-friendly solvents. And when we talk about organic chemistry or organic compounds, all of us know that organic compounds are mostly soluble only in, except sugars and amides, diamides, etc. Other things are soluble only in organic solvents, and most of the organic solvents they are hazardous and they are expensive and they are not eco-friendly, and they're also flammable, so it is little difficult to use. Therefore, there is a need for using some green solvents, and people are looking in for methods of using green solvents. So when we speak of green solvent, now there is a option of using liquid carbon dioxide also as a solvent. Why we are looking into liquid carbon dioxide, and how sustainable is this supercritical carbon dioxide? So I have used an acronym SAC just for convenience, and even though it's not an commonly used, CF is commonly used, but I have used SAC. So why we call it as a sustainable environmental friendly technique? Because it is able to replace the traditional methods, traditional solvents, as some of the solvents are not sustainable. Synthetic ones are sustainable, but if you take any other solvent which we are not able to use for a long term, then we cannot call it as sustainable. But as long as human beings are present and as long as you have vehicles, because carbon dioxide is being let out, so it can be captured in foreign countries. They do have carbon dioxide capture tanks under the ground. So several feet they bore and they capture the carbon dioxide. Though in India and other parts we don't collect this carbon dioxide, but still with maybe in course of time the number of vehicles will be increasing, and when the trees are more cut down, there will be more carbon dioxide and there will be more trapping mechanisms also. So as long as carbon dioxide is available, and as long as human beings are available, we all only take in oxygen and let out carbon dioxide, so definitely it will be a sustainable method. So this carbon dioxide, we are going to restrict this topic to only extraction, how it can be used in extraction process. So for which we need to know what is extraction. In simple words, we can tell it is a process which consists of separating of a substance from a matrix. For a mixture, we are going to remove something outside. So that is what we call as extraction. So what exactly is solvent extraction? Solvent extraction is otherwise called as liquid extraction. You can see the picture, a pictorial representation of the solvent extraction is better to understand. You can see the mixture contains lot of solute molecules, and we are using two liquids of two different immiscible liquids, like it can be an aqueous phase and organic phase, and so using that difference we are able to extract, like one may be water soluble, so that goes into aqueous solution. The other solute may be solvent soluble in organic phase, so we are able to extract it into organic solvent. So the next question comes as to why should we extract a sample? There are several reasons why we need to extract, because if you are working with several tons, it may not be possible. So you need to reduce the size of sample in certain cases. In some other cases, you have a crude sample, we need to select a certain metabolite alone which is significant. So in that case, we go in for extraction where we remove where there's a need of separating the metabolites alone. And we need to have the sample compatible with the analytical technique. So we don't want to take the entire extract and work. And for some of the cleanup process also, we do this extraction. And some cases, in some applications, we are using it for pre-concentration purpose. For concentrating purpose, we can use it. So there are several techniques. Now, the simplest extraction which I can tell you is preparation of tea. So what we exactly do is we take some tea leaves and put it in the, so tea leaf is the solute like, and the solvent is water. So what is getting extracted? Okay, so that brown color is because some metabolite is being extracted into hot water. So that is a simple decoction what we prepare, or brewing. By brewing is the method of extraction. So this we have been using it in our daily life. And nowadays there are research going on in decaffeination of both coffee and tea, because there is a need to remove the excess percentage of, there are different brands of tea and coffee. So we need to remove the excess percentage, or we need to have a limited percentage of caffeine. So people are looking in for better extraction methods, and supercritical carbon dioxide extraction is widely used in this decaffeination of coffee and tea. So I was talking about extraction methods. So one is like simple boiling or brewing tea, etc. There are Several other methods. Infusion, we can also infuse it. Even tea, you can put it inside and you can have an infuser and put inside a hot solvent, or decoction we have already seen, or even digestion. When in UG or PG you might have done gravimetric analysis where you might have digested a sample. So in you just place some precipitate on a water bath. So after, due to that heat, all the suspended particles will settle down. So if you just leave it for half an hour, you know that very minute particles, like you need not centrifuge it. So if you centrifuge, you know that it will, the suspended particles will go down. So like this, the very tiny particles can settle down. So, and it will also help in extraction. Maceration, we need to grind well with little amount of solvent. You can grind it well. So this grinding will help in certain metabolites to be extracted into the liquid. So after grinding, like what we call as in some of the Ayurvedic medicines, we call as kashayams and all. No? So they make this maceration and they do. Percolation. Percolation means you have some holes and you allow the steam vapors to go up, like a coffee filter and all what is being done. So the vapors will go up, it will percolate through the holes and it will be in contact with the solute and it will bring down the extract. Those vapors will collect the extract and come down. And then you have continuous hot extraction. Spelling of continuous is wrong. Excuse me for that. And then continuous hot extraction. You pour the hot extract solvent onto the solute. That hot solvent, when it comes down, it will pull some of the metabolites and it will extract it. Then you have what is called as SCF, supercritical fluid extraction. I'll be coming to that. And then you have microwave and etc. other methods also. So this is one type. This is called as Soxhlate extraction, commonly used when it comes to plant metabolite extraction. So in natural product chemistry, this is widely used and popular method. So you can see that there is an inner orange color container. So it is not exactly orange, it is white color, that is called as a thimble or the container, where inside that we have to keep the solute. That means let us say the plant compound. It can be the bark of a plant, or it can be the seed or leaves or whatever it is. Whether it is any part of the plant, you have to shred it well, powder it well, and then put it in packets. Or if it is a thimble, you can directly fill this portion. It looks like a boiling test tube. Okay, so inside that it is actually porous one. Okay, so you have to keep the plant part inside, the powdered one you have to keep inside, and the solvent will be heated here. So as the solvent goes up, you can see that the hot solvent goes up and you have a condenser here. So the vapors will go up, and because the condenser is there, it will condense and fall onto the plant part. So it will get extracted. So the orange color means that the solvent has now extracted and the metabolite will come. So as the tube rises, okay, so you have some side tubes. So once it rises up, the solvent goes up, it condenses, falls on the plant part, and once it is rising up, when it reaches here, due to capillary action, it will rise up, and then when it reaches here, it will come down. So you get back the solvent also. Again, the solvent goes up. So this process repeatedly goes on, and every time hot solvent falls on the plant part, it will extract the metabolite and it will fall back to the RB flask. So if you are starting with a colorless solvent, most of the organic solvents are colorless. So let us say you have taken alcohol in it. You can see that maybe after half an hour or 1 hour, the alcohol is colored, which means that the extraction process is going on. So it is successful, or the solvent is also it is also successfully extracting the metabolite. Then what we need to do is we need to distill off the solvent, so you will be left with the extract. So this is one method of solvent extraction. But what are the, see, this is in a small scale. Even in a larger scale, you cannot extend the method to a very bulk quantity. This is all glassware, which I'm showing you. Okay, so there are some limitations. Maybe for some pharmaceutical uses, they may use such methods. When it comes to bulk preparation or manufacture, these techniques may not be helpful. And the other thing is, most of the organic solvents, they are flammable. Let us say you want some non-polar extraction like hexane extract, petroleum ether extract. You have to be very careful because they are all very volatile volatile and they are very highly flammable, and they are also expensive solvents. And sometimes you may start with 3 or 4 liters, but when it is recovered, you can see only 2 liters. The other 2 liters would have been, since it is volatile, it would have evaporated. So it will be a loss of solvent also. And sometimes the extraction also may not be very efficient with such solvents and all. And so much of current and other things are used. So it also depends. And the biggest drawback will be when we are heating, it is likely that the metabolite may be degraded, because some of the metabolites which are not stable, let us say some essential oils, I will be showing some picture like it is called some, I'm not sure of the name of the leaf. When it comes, I will show you. It's called Karpuravalli in Tamil. So this Karpuravalli leaves, it is used to treat cold, even to just born or infants. Now they use these leaves. They put it on the chest of the child so that it cures, the child is cured of the phlegm formation in the chest. So why does that happen? That healing power of this leaf is because of the essential oil present in the leaf. Such essential oils need to be extracted. And when essential oils are extracted, you will see that you get the concentrate in less quantities. When if we those who have visited Ooty, you'll know that along the sides they will sell all the essential oils and small tea tree oil, etc. So such essential oils, how do they extract? Steam distillation, or we have to go in for Dienstock distillation, which are all tedious methods, because it is very difficult to distill essential oil. And if we, without knowing the procedure, if those are not experienced, if you do that, you will be actually evaporating the essential oil along with the solvent. So such methods may degrade the compound. We are interested in some metabolite. So if that degrades while heating, so we have to look in for some methods which are more safe, environmental friendly, at the same time they are also friendly with the metabolite which we are dealing with. And such technique is supercritical extraction. So what is supercritical extraction? We are using supercritical fluids for the extraction process. So in that case, we need to know what is supercritical fluid. So we have what is called as a critical point. And above that critical point, those substances above that point, they can be called as supercritical fluids. So now we need to know what is a critical point. So at certain temperature and pressure conditions, if you take the liquid phase of a substance and the vapor phase of a substance, they will be distinctly seen at the liquid. Some phase will have a separate temperature and this pressure condition, and vapor phase also will be distinctly seen. That means you can see it is a liquid, you can see it is a vapor. But as you increase the temperature and pressure condition, there is a stage where both the phases, that is the liquid and the vapor phase of a substance, they become distinguished. We are no longer able to distinguish or find out the difference between the liquid and vapor phase. Such a point we call as a critical point, and substances above this critical point, they are called as supercritical fluids. So here you can see that when you heat a solid, as the temperature increases, at one point it will become a liquid, and then we keep on increasing the temperature. So this is a temperature increase and this is a pressure increase. So there is a point where we are no longer able to distinguish between the liquid and the gas, that is the liquid and the vapor phase. So such a point we call as a critical point, and substances above this critical point, they are called as supercritical fluids. So some of the supercritical conditions for carbon dioxide is highlighted here, you can see. And this picture very clearly tells us that as we increase the temperature and pressure, earlier we are able to see the line, the meniscus is seen. Okay, so that is the demarcation between the gas phase and the liquid phase. And when the temperature slightly increases, still we are able to see the meniscus. So again we are increasing the temperature. Now it is little it is getting merged, but still that meniscus is seen. But at one stage, the point which we call as a critical point, it becomes indistinguishable. It is no longer solid or liquid phase. Both the phases look the same. Such a stage is called as a critical point, and the substance at this stage is called as a supercritical fluid. So you can see the line here, and here it is now 27.3 degrees Celsius. See, you can see the temperature increasing. It is just an image to just tell us that, to show the start point of liquid carbon dioxide. And how, as the temperature rises, the carbon dioxide evaporates, and slowly at one stage with much more increase in temperature, both will become indistinguishable. Now, why we are too much interested in such supercritical fluids is because the properties are also different. Now, the physical and thermal properties of such supercritical fluids, they are in between the pure liquid and gas, because it's a combination of liquid and gas, and we said that one temperature liquid and gas become indistinguishable. So the properties are also in between that of a liquid and gas, and that fetches us a lot of properties. And because of this, these supercritical fluids are otherwise called as dense gases or compressible liquids. And such fluids, they will have good solvation power, and in fact the density will be 100 to 1000 times greater than that of gases. They are not typical gases, but 1000 times density will be more than that of gases. Surface tension will be reduced. The viscosity is also very low, and it has got very high penetration power. That is why it is acts as a very good extractor. So this is just a comparison of like the oxalate extraction which I told you, and the supercritical fluid extraction. Let us take the conventional extraction method, where you have the solvent, and the solvent will pass through the solid, like the oxalate extraction which I showed. And as the solvent passes through the solvent, it will dissolve the metabolite, and you will get the extract and the raffinate, which is called as a solvent. In the case of supercritical solvent, the supercritical solvent will pass through the solids and it will dissolve the solute, and here also you will get the extract, and the supercritical solvent will be the raffinate. So we can say it is similar to that of extraction. The only thing is that here the raffinate will be the reused solvent, and here it will be the supercritical carbon dioxide. So use of these supercritical fluids for extraction, that we call as supercritical fluid extraction. So we can say it is a process of separating one component from the other using supercritical fluids as the extracting solvent. And this extraction method, that is supercritical fluid extraction, it is based on utilization under critical conditions. So for each of the supercritical fluids, you have different supercritical conditions, and therefore it is a technology which is successfully nowadays being used for extraction and purification purpose also for a variety of compounds. And particularly, as I said, it will not degrade the solute. Therefore, in cases like essential oils or compounds where which has got low volatility, this technique is very much useful. And sometimes you have legal limitations, like for example, I told you benzene is banned. It cannot be used. In such cases, it can replace the conventional solvents like benzene. And since it facilitates mass transfer and it allows environmentally friendly operation, this supercritical fluid extraction is most advocated green extraction method. Now let us come to the steps of the green technology. So initially what is being done is we are introducing the feed into the extractor, and then you'll have to pass the carbon dioxide. I will just show you a schematic diagram also. So when carbon dioxide is passed in, the mixing of solute takes place with the carbon dioxide. Supercritical carbon dioxide. So conditions, that is exposure of this phase to 50 to 500 atmosphere and ambient temperature near 300 degrees Celsius, you are able to extract the solute or the metabolite, and we are able to get it by removal of the supercritical carbon dioxide. So we are able to isolate the dissolved solution by precipitation. So this is the component of the extractor. So as told, you can see carbon dioxide will be in a cylinder, and then you have pumps which will help us in taking this carbon dioxide to the extraction cell. Extraction cell is mostly it's like a stainless steel only, or any metal which can withstand the pressure. And there it will get extracted, and then it goes to a restrictor which will maintain the pressure conditions. And then after extraction, we have to remove the solute which will be collected in the collection vial, and then you can get the carbon dioxide separated. So we'll see the parts one by one. The first part is the gas cylinder when it comes to carbon dioxide, or if it is a fluid, you should have a fluid reservoir. The second component is the pump, which is normally a syringe pump is used so that the flow is regulated. So the first part will be the fluid reservoir, second part is the pump. And the third part is the extraction cell, which I mentioned can be a stainless steel chamber or a compartment which can withstand high pressure. And sometimes even tubular columns are being used. And then you have a restrictor here. So this is a restrictor, this gray color box, since it's a schematic diagram, I just shown as boxes, and that restrictor will maintain the pressure changes inside the extraction vessel. And then you have the collector and the detectors. So this is how the extraction takes place. So we can see that carbon dioxide comes out, liquid carbon dioxide comes out from the carbon dioxide tank. It is then pumped inside. The blue color is the gas, liquid carbon dioxide. And here you have a vessel which is having the green color portion is the solid or the feed compound. And then the feed can be added through this input. So once the supercritical carbon dioxide goes, here you have the pressure conditions. You can see that it is getting collected here. You have a cyclone separator, and then finally it is the collection vessel. So this continuously, it helps in the extraction of the compound. Now, what are the modes of supercritical fluid extraction? Two things can happen. Like in tea coffee preparation, there are two ways. Either what we do is we take a tea bag and dip it in a cup of water, or in the case of a coffee maker, you will percolate the liquid through it. Likewise, the sample can be soaked in a supercritical fluid, just like we keep the tea bag, and it will be extracted. So you have a carbon dioxide, liquid carbon dioxide as a fluid, and inside that you have to keep the sample matrix. So from the sample, the metabolite will come out into the supercritical fluid. The other way is that we can have the sample and pass, just like what we have seen now. We can have the sample in an extractor and pass continuously liquid carbon dioxide. So that is similar to that of a coffee maker. So some conditions which are required, as in the case of dried ginger, how suppose we use dried ginger, what will be the extract or what is the need? We need to get the ginger flavor. So some of the powders also we see they just with one drop we are able to get that flavor, the lemon extract and all we say. So that is how, because they are able to use this extraction and they get the concentrated one. So since it is highly concentrated, we use just a half a drop or so, we get that flavor. So in such things you can see dried ginger, which gives ginger flavor, solvent which can be liquid carbon dioxide, and these are the pressure conditions which we can use. So for first extraction you have to maintain this temperature and pressure, and for second extraction you have to maintain this pressure and temperature. And for coriander seeds, to get the flavor, you can use same supercritical carbon dioxide, and here also the pressure temperature conditions you can see. And it is not only for the essential oils or for such things, even for egg yolk, to extract the phospholipids, supercritical carbon dioxide is being used. So you can see this is a small GIF image where you can see how cinnamon extraction is being conducted by using supercritical carbon dioxide. Nowadays, people are adding the cinnamon, and particularly in COVID time, we go in for more of spices. So we need to have small quantities of these spices in our tea or in some hot liquid for the immunity purpose. So here, particularly supercritical carbon dioxide is being used. Like in the extraction of vanilla also. So dry ice is used. Now let us come to the advantages of it. As I already told you, we are replacing the hazardous organic solvents, the traditionally used organic solvents. Some of these solvents we cannot store it, and some of us know how difficult it is to store petroleum ether, diethyl ether, etc. Even near the electricity boxes and all, you cannot store it. Okay, so there is always the risk of storage of certain organic solvents. And if there is suppose the lid is not closed, you can see in a closed room, the moment when you open, you will get so much of ether vapors, and it has got an anesthetic effect also. So such risk we can reduce by replacing it supercritical carbon dioxide. And the extraction or the procedure is very rapid. As I already told you, the penetration power is high for carbon dioxide. Therefore, several times higher action you can get it. And this technology is useful for extraction and purification of compounds having low volatility. I was mentioning that it will see to that the substance is not degraded. And There is a complete separation of the solvent from the extract and the raffinate. Sometimes when we do the traditional separation using filter paper and all, we see that there is no complete separation. Even that solid will be having that liquid, still the filter paper will be having that traces of the solvent. It will smell of that solvent. And even that solvent will sometimes smell of the solute. But in the case of carbon dioxide, since carbon dioxide is a gas, either after the extraction process you can evaporate the gas or you can recycle it. So this sort of contamination will not be there, and it can be a continuous process. And the handling cost is low, but at the same time the capital cost, once you have to invest, then it will be low. The handling cost will be low, and solvent recovery is easy. Sometimes it is only carbon dioxide, so you can just let it out, and then it is very versatile, and it is very efficient in the sense it can be even used as a co-solvent or a co-solute. But what are the limitations? Sometimes it takes prolonged time also for the for certain types of sample matrix. It will take a longer time, and sometimes scaling may not be possible. And as I said, the capital cost, setting up the plant and other things may be expensive, but handling procedure will be less. And the consistency and reproducibility, since it's a continuous production, one batch may have some yield differences and the other batch may be different. So what are the other, by now we know that it is mainly used in extraction, and already we have seen how it is being used in decaffeination of tea and coffee, that is removing of caffeine from tea or coffee. Where are the other fields? Like one example we saw now, ginger extraction, coriander extracting its flavor, and then extracting phospholipids from egg yolk. And other examples include fat and oil samples in meat, egg meals, etc. And then byproduct recovery also, this supercritical fluid extraction is being used. That is, we have lot of vegetable and fruit waste being converted into vermicomposting or composites, and they are used as manure only. But recently now people are using it for recovering the metabolites by using the supercritical carbon dioxide procedure. So this is just an example to tell you how the food processing industry has been using it to extract omega-3 fatty acids, oleic acid, resveratrol, lycopene, etc. And these are used in to aid different disorder conditions. And this is a paper which has come out in Springer, where I saw that valorization of coffee roasting byproducts is also done by using supercritical carbon dioxide. That is, they're just converting the waste, which is coffee silver skin, is being used. The waste material is being used in efficiently extracting some of the components. And the conditions, because it is the capital cost is small, they have done some mathematical modeling. Here comes the role of computer engineers or software people, or where artificial intelligence can be used, where you can fix the pressure, temperature, concentration conditions, and you can devise the mathematical model, and based on your experiments, pharmaceutical companies or manufacturers can take up the process. This is yet another research paper where I came across that micro encapsulation of lycopene. Lycopene is the metabolite which is present in tomato. So that is also used in anti-cancer studies. So in this paper they have used a supercritical carbon dioxide extraction process. And this is a very recent paper. You can see that it has come out in Antioxidant 2021. And inulin extraction is also done by using this supercritical carbon dioxide extractor, and where they found out that the maximum yield of inulin was 0.8% at the temperature of 40 degrees C and 100 bar. But when supercritical carbon dioxide was used, the yield was much better. So the conventional technique and the supercritical, they have compared. So the authors say that they can be used for extracting inulin from the roots of chicory, as it can be used as a nutraceutical in functional applications. And not only in food industry, this supercritical carbon dioxide is also used in dry cleaning. We know that generally petrol or any other hydrocarbon is being used, like perchloroethylene is most common in dry cleaning, but people are now using liquid carbon dioxide because it is less expensive and it is also eco-friendly. when compared to the hydrocarbons. And plant waxes and oil separation is generally difficult when you use some solvents, but here it is very easy. As I said, that contamination will not be there. And when there's a need to recover hydrocarbons from soils or sediments, supercritical carbon dioxide is being used. And it is also used in determining polyaromatic hydrocarbons and organic pesticides and metals. When it is washed with this supercritical carbon dioxide without degrading the other metabolites present in the vegetables or fruits, only the pesticide, that means selective removal is also possible being in the case of supercritical carbon dioxide. And already I mentioned caffeinating tea and coffee. And these are some of the examples which I have taken from the recent papers. In fact, you can see this is a preprint, it is yet to be published. And why I have taken this paper is that because of the importance of supercritical fluids, there is even a journal which is called as Journal of Supercritical Fluids, and it is in the preprint. It is to be published in 2022. So this involves the supercritical extraction of pinosembrin from a plant, and you can see that for different conditions of temperature and pressure, they have analyzed the content of this pinosembrin, and the authors report that this method is more efficient. And this is yet another example where supercritical carbon dioxide from olive pomace has been used, and it is a semi-solid. This pomace means it is a semi-solid which is a byproduct of this olive oil production, and it is a source of these phytocompounds. And several extraction methods are previously used, and even several freeze drying techniques are used for preparation of this, for extraction of this olive pomace from the olive oil. By using supercritical carbon dioxide, the authors, this is also come out in Molecules 2021, where they claim that it is a green method and it has got a very good potential. And this potential of olive pomace can be upcycled by using the supercritical carbon dioxide extraction. And it is not only for food industry. I came across a paper in Molecules in 2021 where they have used it for extraction of metals also, precious metals like palladium oxide from aluminosilicate supported catalyst. And like for example, because of the scarcity, precious metals, there is a need for it to be recycled, preferably with the green and energy saving recycling processes. So in Andrea et al., these researchers, they were able to extract palladium using supercritical carbon dioxide by also using polymers along with the carbon dioxide. And this Marubium vulgar, this is a plant which is being commonly used, and where the authors, it has come out in RSC Advances, and the purpose of me telling about this is some of us might not have come across some of the journals. So at least such things we will be able to refresh our memory about some of the recent journals also. So RSC is one such journal with a good impact factor, and in 2021 they have published this extraction process, SAF extraction, wherein they have got very good yield compared to the oxalate extraction. And why I have mentioned this Marubium is that this is a homeopathic medicine which is sold in the name of the plant only. It's very commonly used to relieve cough and bronchial problems, etc. And this plant, by conventional technique, there is a possibility that the metabolites are degraded because of temperature. So it is supercritical carbon dioxide is efficiently used for this. And yet another paper has come out in 2021 in biointerface research and applied chemistry, where they have used for the extraction of black nightshade berries. And perilla is the one which I was telling you, which is called as Karpuravalli in Tamil, and it is used to treat for even in cough and cold and for born infants and all. We just put it on their chest. So here also, the authors, they have done some theoretical work also to establish its modeling of the temperature pressure conditions. So this particular paper, why I have mentioned this, some of us may think that we are in the engineering field and we may not have access to the extraction methods or what is the need, because it involves laboratory procedure. But I came across this paper in chemical engineering communications where they have just theoretically worked out on modeling the procedure, that is the supercritical extraction, the temperature pressure conditions by response surface modeling RSM technique, and you have certain softwares also freely available. So we just need to go to such papers, refer, and we can ourselves create some models. And this paper is particularly for the engineering faculty. So with this, I think I have done some justice in talking about the supercritical fluid extraction. And I thank once again the organizers and the participants, and I will be happy if you have some questions which I can take up.
Thank you. Thank you so much, madam.
Thank you, sir.
Dear participants, if you have any queries or questions, put it in the chat box. Yes, I think there is no questions regarding this
As
question.
usual, yes, sir. This is a new topic also. And as I feel that particularly the last two slides was because they think that supercritical they may not use for the research field, but I think even engineering people can go in for several papers. Mathematical modeling is there. And there's a question from Dr. Dinesh as to whether it is expensive. The capital cost may be expensive. It is in double-digit lakhs only, but after that, the handling cost is very less. And it will compensate the yield and the purification. See, in the ordinary, when we use organic solvents, the workup is tedious. And mostly we end up with, as I was telling you, if you take a mixture of A and B, mostly even the smell of B will be in A or the smell of A will be in B. But in the case of supercritical, this contamination can be avoided and purity factor will be an advantageous when considered to the cost factor.
This, Madam, what you explained that the supercritical point.
Yes, sir.
What we cannot able to distinguish the different phases.
Liquid and
is
gas.
A very amazing concept, madam. And session is very good, informative.
Thank you.
What you the carbon dioxide extraction process, that is very nice actually. I take this opportunity to thank today's speaker, Dr. P. Lalitha Madam, for considering our request to spend your valuable time and share your knowledge with our participants. Thank you very much, Madam.
Thank you, sir, and thank you, participants.
As a token of gratitude on behalf of management, principal, dean, and director, and organizing committee, we are hereby sharing the appreciation certificate to the speaker. Please accept it, madam.
Thank you, sir. Thank you for the certificate. And once again, thank you to the organizers.
We will mail this appreciation certificate through your mail, ma'am.
Yes.
With the permission of the speaker, we are going to end the session.
Yeah. Thank you, sir. Can I leave the session?
Yeah. Okay.
Thank you so much, ma'am.
Thank you, Dr. Krishna.
It was very nice, ma'am. It was very nice. It came out very well, ma'am. Even we are receiving in the chat, we are receiving it as informative session. And thank you so much. Nice. And a very informative, very nice session we are receiving, ma'am. Thank you so much, ma'am.
Thank you.
Thank you so much, ma'am. Yeah. Thank you. Okay. So, participants, you can get feedback link in chat box. We will post the feedback link in group also, just to fill it. And afternoon session will start by 1:55 itself. Please do join. For the afternoon session,
this provided session. See you live on the paper.
Okay. Thanks for patient listening. Thank you so much.
Feedback from LinkedIn.